didn't see you. Well, today we'll be watching a string vibrate on an instrument. For example, when it does vibrate, it makes noise that travels to your ears through the air. And so what happens is the specific string will oscillate at a frequency that is usually much too fast for the human eye to catch. And this will create the music which we so much to enjoy listening to. Well, we are going to use a slow motion camera to catch or watch this oscillations of the string. And so therefore we'll be able to see just how fast it does this and what exactly goes on in an occurrence we can no longer catch with our naked eye.
So let's try this with the piano at regular film speed. You're going to want to look for the fourth string from the right on this piano, which is a C1. The amplitude is not very great because it's a piano, and the frequency is high enough that it's hard to see.
At 1,000 frames per second, it's a lot easier to see the amplitude and frequency, but it's still not enough to get good data from. As you watch the video, notice the oscillation traveling up and down the strings.
In this video of a double bass playing the same pitch, C1, the frequency is the same because the pitch is the same. Frequency, measured in hertz, is defined as the number of oscillations per second that occur. However, on this bass string, the amplitude, or the distance from the midpoint to the trough or peak of the oscillation's motion, is greater. The amplitude is connected to the energy in the sound, and with the higher amplitude, more energy, which we interpret as volume, is output. Notice that the camera makes a wave-like formation appear in the string at this regular speed. That's an artifact of the video because of the number of frames per second, and is not how the string actually appears when it vibrates.
At 1,000 frames per second, the vibration of the C string is much more visible than it was before. Also notice that the amplitude of the C string is much greater than it was on the piano. It means also there was much more energy involved in the vibration of the C string. There's also the resignation of my G string, which we'll talk about later.
This tracker program can be used to watch the string oscillate, and it'll track whenever the string reaches its farthest distances away from equilibrium, either to the left or to the right. The time it takes to move between these positions can be used to find the frequency of the string.
Using the tracker data, we found the period to be 1.05 seconds per oscillation. This was recorded at 1,000 frames per second and played back at 29 frames per second, which ends up being a 34.483 times slowdown. Frequency is 1 over your period, and so the frequency of the string is 0.952 oscillations per second in slow motion. So to find it at regular speed, we multiply it by the slowdown and get 32.8 hertz at regular speed for the frequency.
Wolfram Alpha gives a pitch of 32.7 hertz for the value of C1, and so when compared with our experimental value of 32.8 hertz, we come out to a 0.31% error. Just one last thing. When a string's frequency is multiplied by successive whole numbers, an overtone series is created. At the second overtone, the fundamental, or the pitch of the open string, is multiplied by a factor of 3. 3 times the pitch of this open C is an octave and a fifth above, which is coincidentally the same as the G string, the fourth string to the right. Note that this G string appears to oscillate about 3 times as fast because it has 3 times the frequency of the open C string.